Well, that concludes the first part of the talk, where we look at enhanced dispersivity and sort of plume scale heterogeneity. And what I want to do now is shift to the second part of the talk, where we're going to look at the variability of the retardation factor, the increase in the retardation factor of that original plume with time or distance of travel. And here's shown what happened. The retardation factor initially was cataloged at something below 2 and increased to close to 6 throughout the 2 years of that experiment. There's a way that we can predict the retardation factor empirically, and we do that based on the organic carbon content of the sediment, which in this aquifer is on average 0.02%. The KOC, we call it, which is the organic carbon normalized distribution coefficient for PCE, which we can look up in this case based on many other measurements and other systems. This is a tabulated value, and the value I've used here is just from an EPA listing. And we can predict a KD and then predict a retardation factor from that. That's the typical model that we use when we use many of our existing contaminant transport models for organic pollutants. And it predicts a retardation factor of about 1.5. And so you can see that the empirical model that we employ many times for this chemical underpredicts the true retardation by a factor of 2 initially and a factor of about 4 at the end of the experiment, which if you're thinking in volumes of water flushed, is not an insignificant amount. What I want to get you to think about with me now is what really is the sorbent that causes this retardation of the contaminants in this aquifer. Where is it and what are its characteristics? And I'm sorry to tell you that after 20 years of study, we still don't know the answers to this, but we're getting closer. And again, looking at this with the idea of saying, what about this aquifer is actually transferable to other aquifers? Do we think we should expect this kind of behavior elsewhere? So one of the first things that we did was to look at sorption isotherms for PCE in this aquifer. And that means that we're looking at the sorbed concentration of PCE versus the solution concentration. These are the batch experiments like I showed you before, and now we're looking at a range of many concentrations. Each one of these spots is one of those little batch experiment files. And we're looking at a very wide range in concentration here. The high end is near the solubility of PCE, and because PCE is often used as a pure oil in industrial work and often released as a nearly pure oil, those are the concentrations you would expect to find in groundwater immediately adjacent to an oil blob or an oil body. But the water quality standards for drinking water tend to be down here in the range of 5 to 50 micrograms per liter. And so as groundwater scientists, we're interested in this whole range of concentration from below 5 microgram per liter up to 240,000 or so microgram per liter. Additionally, I think we learn a lot more by looking at a broad range in concentration than by just looking at a narrow band of concentration. Again, I'm comparing the real data, the measured data, to the empirical prediction. And you can see again that the empirical prediction, the same type of prediction that I showed you on the previous slide, is lower than it should be for all concentrations, and that in fact the slope of the two lines differs, and that's important. This line is fit through the data using a Freundlich isotherm. I get n, or slope of this isotherm, being less than 1 for all the samples that I've measured from this aquifer. And Kf such that the isotherm is always above the empirical prediction, significantly above it. Remember that when C is unit concentration, then essentially Kf is equal to Kd, and you can think about the Kf as you would the Kd, really, if you're more used to thinking about those. I'm just going to call this the sorption coefficient throughout the rest of the talk to make it simple. So to understand what sorption depended on, one of the first things I did was to take a core of Borden sediment and divide it up into 20 subsamples vertically and look at the sorption of PCE in that sample, and I did complete isotherms there, and then compare that to other properties of the sediment. So here we've got sorption coefficient with depth, and here we've got the organic carbon content with depth. Not surprisingly, those two are correlated. Our empirical model suggests that they should be. But then if we keep going, here we've got the carbonate content with depth, and it looks similar too. Now on the next one, we've got the mean grain size, and it looks similar. And the only one that doesn't is the fraction of sediment that is magnetically separable. So basically, this is the magnetite and other iron-bearing mineral content of the sediment. So what I found is that in this aquifer, discouragingly, there's a very confounded set of relationships in that the greater sorption and more nonlinear sorption are correlated to large grain size, high carbon content, and high carbonate content. So what is that about? We can actually break it down into two questions. Why is the carbonate content greatest in the coarsest lithofacies, and why is sorption also greater there? And the first question I can give a geological rationalization to, and that is that if we look at a map of southern Ontario, a base map, we find that we've got the Niagara Escarpment carbonate rocks here, and the Canadian Shield silicate rocks here, and Canadian Forces-based Borden is sitting here at the margin of Glacial Lake Algonquin during the last glacial period. And the sediments were deposited then in a nearshore environment, and so what we find is that the carbonate lithic fragments, which are much physically softer than the silicates, are not present in lithofacies where we can see that we've had a lot of tractional transport during deposition. So in those distinct plane laminated facies, you see that the sediments have been tumbling and experienced a lot of physical erosion and sorting too. So the well-sorted zones have very low carbonate content. The poorly sorted zones, like the massive coarse grain zone, are the zones where the sediment just got dumped. There's not a lot of winnowing and sorting that happened there, and those are the zones that have the carbonates, which are harder, or which are softer, sorry, than the silicates. And so those are the zones where we have the coarse carbonate lithic fragments present. The harder part of the explanation is to think about why sorption is also associated with high carbonate content strata and coarser strata in this particular aquifer. And so I want to do first is clarify a couple of points which colleagues have done research on or which we can do calculations on to suggest that they're not important. The first thing is that you might want to say, well, then PCE must be sorbing to carbonate minerals. That's not the case. Studies of a hydrophobic chemical, which isn't very soluble like PCE, to pure carbonate, calcium carbonate, show that the attraction is very low, sorption is very low. It's not surprising because carbonate mineral surfaces then would tend to be ionic surfaces. So that can't explain the sort of excess sorption that we see, not carbonate mineral directly. The second thing is that sometimes for hydrophobic pollutants, we want to invoke the importance of clay minerals for sorption of these chemicals. And I won't dispute that there are clay minerals that are important for sorption of these chemicals, but they're not present in this aquifer. And the clay minerals that are present at very low concentrations, when again we look at pure mineral sorption studies with PCE and those kinds of clay minerals, the values are so low that they can't be important here. So we're left with, I think, thinking about the importance of the carbonaceous matter. What do I mean by carbonaceous matter? First of all, I mean all carbon-containing non-carbonate matter. Why am I not just calling it organic matter? Because there's stuff in there that isn't organic anymore, like soot or char, for example, might be important, but it's pretty hard to claim that they're organic. What I'm showing you here now is what we call an extract of total Borden sand carbonaceous matter. When this kind of an extract is done, it's done with high concentrations of strong acids and with heat. And it's the same way that this is basically the coal petrography techniques applied to aquifer sand. And so what we find here is that there are various constituents of what we might call hard carbonaceous matter, such as this shiny material here, the shiny spots here, and the shiny material here. And on the right side, what we're seeing is something that I'm going to classify for the moment as soft organic matter, and it's the material that fluoresces in the fluorescence mode. And this is actually the same figure. You can see this is the amorphous or soft matter, and this part here that is black in the fluorescent light is the hard matter. Now, what do I mean by hard and soft? before I go forward, let me remember to tell you that the point of this slide is also just to show you the wide variety of carbonaceous matter that's present in these sediments. And this is just a few of the pictures. This is what I mean by hard and soft. It's a functional distinction between two types of sorption behavior, really. Absorption of PCE occurs to the, we think, soft organic matter. And this is basically the empirical model that many of us are used to using in our groundwater transport models. Soft organic matter is characterized by having a fair amount of polar functional groups, oxygen, hydrogen, and so on. As I said, our empirical approach seems to work. Sorption isotherms tend to have a slope of 1, so the concentration dependence is linear. An example of this behavior is a humic acid, and this is a volume-based process. So the PCE can diffuse right into that organic matter. Adsorption, though, is something that's a little newer on the scene in the organic contaminant world. It's not brand new, but we're still not using it routinely because I think we're still not sure how or when we should. We can describe this as a surface process, and I've drawn it here as a very sharp and angular surface. It's in fact probably a very irregular surface on this hard matter, but this is undoubtedly a surface process. The composition of this material is aromatic. When we do sorption studies with model materials in the laboratory, like char or coal, hard coal, we find that we get anomalously high sorption coefficients compared to the empirical model, that the Freundlich type isotherms are always less than 1, so they're very, very concentration dependent isotherms. Some examples of this material are soot and char and hard coal. To give you a feel for how this works, the sorption coefficient per gram of carbon here can be 100 or 1,000 times greater than it is here. So just a little bit of this can cause it to be more important as a sorbent than this in many systems, we think. So if I think about modeling all my sorption isotherms in the Borden aquifer, all those 20 isotherms from different locations, using what we might call a dual mode model where I have an adsorbent contribution and an absorbent contribution, this is the kind of result that I get. And I'm just showing you the model result from the 50 centimeter sample. Just took the one right in the middle. And now what you're seeing, again, these are the observations. The pink dots are the observations. The pink line is the total model, and it's the sum of the adsorption or hard carbon portion plus the absorption or soft carbon portion of sorption. So what we find is that the adsorbent process dominates the process when we're at or below about 10 milligrams per liter in all of the different samples. And that the absorption process, which is basically our empirical process that we usually use, is actually only dominant in the very highest concentration ranges. When these sites are saturated, they become less important than the black line, which is more important now. That's the absorption process.